So I have already sent a problem with his solution. Now I am going to explain in this video the solution of this problem. So before going to that problem, we just remember the last class, okay, what we discussed in the last class. So in the last class, you see, if I consider this product 1 plus z square plus dot 1 plus z square plus z to the power 4 plus dot. Similarly, next one will be 1 plus z cube, z to the power 6 dot. Next one will be proceeding in this way. The nth term 1 plus z to the power n plus z to the power twice n plus this dot. That is continuation. Okay, so this is the product of this infinite product. Okay, product of this infinite number of series. So if I expand this product, then you can see last class we discussed already. So coefficient of z to the power n, is nothing but partition of n. Okay, how many partitions of n are there? So this is nothing but a coefficient of z to the power n. So therefore this expression can be written as summation n is n greater than equal to 0 p n z to the power n. Okay, so this expression can be written in this way. So summation n is greater than equal to p n z to the power n. But this is nothing but actually this first sum is nothing but infinite sum is nothing but series is nothing but 1 by 1 minus z. Next one will be 1 minus z square. So you can write down this expression in this way: 1 by 5, that is product I is greater than equal to 1 minus z to the power I. Okay, so this is one result we discussed in the last class. Then we discuss another result. So number of actually distinct partition of n. Okay, so for number of distinct partition of n, we have this result: distinct partition 1 plus z square. We need if I expand this 1 plus z square 1 plus z cube, then the coefficient of n is nothing but the number of distinct partition of n. Therefore this product can be written in this summation sign. Okay, so this is another result. So the product can be I is greater than equal to 1 plus z to the power I. Okay, so this we have already discussed in our last class. Okay, number of distinct partitions. So this concept is going to introduce here in our discussion. So there is another concept we have to remember. Okay, another concept, that is the self-conjugate partitions, and how many self-conjugate partitions are there. Okay, self-conjugate partition of n. So self-conjugate partition, self-conjugate partition means so conjugate, first you remember the conjugate partition. So conjugate partition is nothing but, if I consider partition 5 4 3 2 1, okay, this is a partition of 9 12 14 15. This is a partition of 14 15. Then this is the corresponding Ferris diagram. First row 5 dot, second row 4 dot, 3 dot, 2 dot, 1 dot. So this is the corresponding Ferris diagram lambda, and the corresponding conjugate partition just interchange rows and column. That is, first row will be first column. So if I interchange rows and column, then you will get this partition lambda star. But here you can see lambda is equal to lambda star. So this type of partitions are said to be self-conjugate partition. Okay, self-conjugate partitions. So here how many rows are there? 1 2 3 4 5. So here also you can observe 4 rows and something like that. So self-conjugate, this is an example of self-conjugate partition. So now how you can count the number of self-conjugate partition by using the concept of hook actually. Okay, using the concept of hook. So this is a self-conjugate partition. This is the 5 4 3 2 1. So you just consider the Ferris diagram, and this is the corresponding Ferris diagram. Then you just consider the hooks actually. How many hooks are there? There are 3 hooks. 3 hooks are there. In the first hook, how many dots are there? There are 9 dots. In the second hook, there are 3 plus 2, that is 5 dots. And the third hook, there are 1 dot. That is, this is again a partition of 15. This is a partition of 15. This is a self-conjugate partition. Okay, this is self-conjugate partition. And you can see this is you can have this partition of 15 because the hooks in this hook we counted all the dots, so automatically this is a partition of actually 15. Okay, partition of 15, and that is this and this hook contains how many dots are there in the first hook. That is there are 5 plus 4 9, then 3 plus 2 that is 5 1 9 5 1 9 5 1. Okay, 9 5 1. Nine 9 5 1. So this is a partition. This is a partition of again 15. Okay, where the parts are odd. 9 5 1. These are odd parts. Okay, so there is actually one-to-one correspondence between the self-conjugate partition and the number of partition of n, say, where the parts are odd and distinct. Parts are odd and distinct. So there is a one-to-one correspondence. So this is the corresponding one-to-one correspondence. You just consider a self-conjugate partition. You draw the Ferris diagram, and you just consider corresponding hook. Okay, corresponding hook. So the hook will represent the corresponding partition of n, where the parts are odd and distinct. Okay, this is the corresponding one-to-one correspondence. Okay, so this concept we are going to use in our problem. Okay, so what is the problem here now? The problem is you have to establish this result. Okay, we have to establish this result. So product of 1 plus z to the power twice I minus 1, I is greater than equal to 1, equal to summation k greater than equal to 0, z to the power k square divided by product of 1 minus z to the power twice I from 1 to k. Okay, so this is the question. So this sum product is equal to this sum. We are going to establish this result. So to establish this result, we will use the concept of self-conjugate partition. So suppose self-conjugate partition. Suppose, so because this expression, if you remember this expression, nothing plus 1 plus z, first time will be, next time will be 1 plus z cube, next time will be 1 plus z to the power 5, something like that. So you just see this last class second result. So you can see second result, this result. Okay, so this expression can be written in this way. So z to the power I. Okay, so that is, this is PD of n, that is distinct partition of n. But here z to the power twice I minus 1, that is odd, the parts are odd. Okay, so therefore this expression is nothing but, this product is nothing but this product can be written as if I take the coefficient of z to the power n, so the coefficient of z to the power n is nothing but this will represent the partition of n where the parts are odd and distinct. Okay, where the parts are odd and distinct. Okay, so this we have this result. Actually already we have this result. Okay, parts are odd and distinct. Okay, so parts are odd and distinct. Already we have established that self-conjugate partition is same as that of the partition with all parts are odd and distinct. So this is actually in our discussion, this is actually partition of n where the parts are odd and distinct, but parts are odd and distinct is same with self-conjugate partition, so we can replace this. Okay, so PSC of n, self-conjugate partitions, PSC of n means number of partitions which are self-conjugate. So this we can write this expression. Okay, write this expression. So you see this picture. Okay, it is okay. So see this picture. This is the picture. Okay, here z to the power twice I minus 1. This will be odd and distinct. So but odd and distinct is nothing but self-conjugate partition. So this is the first expression we have. Okay, now we are going to count this self conjugate partition in another way by using the concept of Darby square. So Darby square. So what is the concept of Darby square? So you just consider the self conjugate partition. This is a self conjugate partition. Okay, and you consider the largest square in the upper left corner. This is the largest square upper left corner of the Ferris diagram. Then this is the largest square, this is 3 by 3 square. Okay, in general, if I consider the largest square of the from k by k, say k by here k is equal to 3, so in this example k is equal to 3, this is the Darby square. Then you can see how many remaining dots are there. There are actually here so all total there are n dots, because this dots represent the partition of n. Okay, so there are n dots. So Darby square contains k square dot, so you have to delete this k square dot, that is n minus k square. So how many dots are remaining dots are there? N minus k square. But this below this Darby square, this dot n, right side of this Darby square, this dot, this will represent the same partition. You can see these are nothing but the same partitions, 4 2 1. This is also 4 2 1. Okay, same partitions. Okay, so and it contains at most k parts. Each of this partition, after deleting this k square dot, each of this partition, that is partition of n k square divided by 2, this is not 3, n k square divided by 2, each of this partition, this and this, okay, are the same partition, and each of this partition contains at most k dots. Okay, at most k dots. Okay, k dots, at most k dot. It may contains at most k dot. It is not possible that they can contains more than k dots. Okay, because we have already deleted this Darby square of k by k. Okay, k by k. Okay, so therefore you see at most k dots. So the partition of n k square divided by 2 on the right and below the square are the same, and number of parts is at most k. Okay, number of parts is at most k. Number of how many parts are there, not dots actually, number of parts, how many parts are there, how many parts there are at most k. Okay, there are 3 parts, here also there are 3 parts. Okay, there are 3 parts. So these are the they are actually they contain at most k parts. It is easy to notice this actually, how this contains at most 3 parts. Here also we have 3 parts, here also 3 parts. Okay, so at most 3, so it may be less than 3. So okay, if this contains only 1 dot, if these dots are not there, then this contains actually 2 parts. This contains actually 2 parts. If these 2 dots are not there in the last hook, if there is only 1 dot, then these two this part contains this partition contains only 2 parts. Here also this partition contains 2 parts, but it is a 3 by 3 Darby square. So in this case number of parts is less than k. Okay, so therefore it contains at most k parts. So the partition of n minus k square, divided by 2 on the right and below the square are the same, and the number of parts is at most k. Okay, so for fixed k, the contribution to self conjugate partition is therefore the coefficient of z to the power n minus k square divided by 2. Okay, z to the power, and since there are at most k parts of that partition, of each of that partition, so you have to consider this expression from the last class, 1 minus z square, 1 minus z to the power k. This is the coefficient of z to the power n minus k square divided by 2, because each partition contribute to the self conjugate partition. Okay, so each coefficient of each partition of coefficient of z to the power n minus k square divided by 2 contribute to the corresponding self conjugate partition. So for fixed k, this is the contribution. Just you consider this product 1 by this and take the coefficient of z to the power n minus k square divided by 2, because the each of these partitions contains n minus k square divided by 2 members. Okay, so substituting z by z square, we can have this. Okay, z by z square, we can have this, and this is nothing but replacing n minus k square by n, so this will give this. Okay, this will give this. So if I take the sum, this is nothing but the coefficient of z to the power n. So if I take the sum, this is nothing but coefficient of z to the power n in the left hand side. Okay, left hand side, this is the coefficient of z to the power n in the left hand side. This is nothing but already coefficient. This is self conjugate partition of n. Okay, z to the power n. So left hand side will represent this part, and right hand side, this is the right hand side, k greater than or equal to 0, summing z to the power k square 1 minus z square 1 minus z to the power 4 up to z to the power twice k. So this will get the required result. From this expression, you just replace this summation sign in terms of product, so we can have this result. Okay, so this is the required result. So you see this video, and if there is any problem, you can discuss with me.